Hello everyone. I'd like to welcome all of you for another video tutorial session for the drug designing laboratory course. And in this session, I am going to demonstrate you how to use LigBuilder for performing de novo ligand design. Okay, so before seeing the various steps, right? So let me tell what is de novo ligand design. So first, let me tell what is meant by de novo ligand design. So de novo ligand design is a kind of structure-based drug design. So we should know the 3D structure of the drug target. So let me draw this and assume that this is the 3D structure of the drug target. So if it is a druggable target, it will have some space for binding the incoming ligand molecule. Say this is the binding site of this protein molecule. So if we design any ligand molecule using computer algorithm which can fit inside the binding site of this protein molecule, having the knowledge about 3D structure of the drug target as well as the binding pocket, then that approach is what is called as the de novo ligand design. So designing the ligand molecule based on 3D structure and architecture of the binding pocket of the drug target. That is what is called as de novo ligand design. There are many computer algorithms we can use for de novo ligand design. So for this session, I am going to demonstrate using LigBuilder, which is a freely available software, which is very promising software for de novo ligand design. Okay, so this is the overview of de novo ligand design. So the same slide which I used for discussing the drug designing theory course. So here, so the first step is that we have to make the crystal. So we have to determine the 3D structure of the protein complex with the ligand molecule. So if we go for X-ray crystallography, so the very first step is going to be we have to make the crystal between the protein molecule and the ligand molecule. So once if we made the crystal, so we can determine the crystal structure. We can determine the 3D structure of the drug target complexed with the ligand molecule. So once if we got the complex structure, once if we know the 3D structure of the protein along with the ligand molecule, co-crystallized ligand molecule, the next step is we can easily identify the binding site. The place where the ligand co-crystallized, that place could be the binding site, and we can identify what are the various interactions which are taking place between the drug target and the ligand molecule. So then we can remove the protein and the ligand molecule separately. Okay, so we can use even PyMol or any other software for separating this protein ligand complex into individual protein molecule and the ligand molecule. So then once if you remove the ligand molecule from the binding site, and once if you have the details of the binding site amino acid and the binding interaction, so this is called as identification of the pharmacophore feature. So once if you know the pharmacophore feature of the drug target and the ligand molecule, so once if you remove the ligand from the binding site, so based on the knowledge about this pharmacophoric feature, so we can design the ligand molecules, new ligand molecules which can fit inside the binding site and which can complement with the pharmacophore feature which are required for good interaction between the drug target and the ligand molecule. Then we can calculate or estimate the binding strength, we can calculate the binding affinity, we can calculate the free energy. Then we can look for the possibility of synthesizing the potential compound through synthetic chemistry. So if that molecule is promising or if it lacks potency, then we can improvise by optimizing the structure using the structure-based drug design, right? So these are the various steps of de novo ligand design. So let me erase the annotation. Yeah. So coming to the LigBuilder, so let me show what are the various steps of LigBuilder. So here, so first step of LigBuilder is that we have to take the target protein molecule, and we have to choose the protein which is already co-crystallized with some ligand molecule, and we have to separate the protein and ligand. So we have to keep the protein molecule separately and the ligand molecule separately. Then we have to run this pocket. So the input for this pocket algorithm is the information about the protein molecule and the ligand molecule. So we have to input the protein molecule in its PDB file format and the ligand molecule in its mol2 file format, and we have to execute this program Pocket. Pocket is one of the program of LigBuilder. So once if we execute the Pocket program, so it will calculate the pharmacophore feature of the protein as well as the ligand molecule, and that information will be taken further for either grow or link. So we can say that the LigBuilder is having two approaches for building the new ligand molecule. The first approach is called as grow approach. The second approach is called as the link approach. So both are independent. We can either go with grow approach, or we can go with the link approach. So both will lead for design of novel new ligand molecules. Okay, finally we will get many number of ligand molecules which can exactly fit inside the binding pocket of the drug target, which are also complement the pharmacophore feature of the drug target. So this is the overview of the LigBuilder. So let me delete this, and yeah. So once if we run the pocket algorithm, so what will be the output? So the output from the pocket algorithm, the input for the pocket algorithm is we have to input the protein molecule along with the ligand molecule, not as a single file, as a two individual files, protein and ligand separately we have to input, and this pocket algorithm will calculate the pharmacophore feature. You will finally get some map like this, a grid like this. So here each color represents the pharmacophore feature of the protein molecule and the ligand molecule. So this will be the output from, so these are the output A, B, C and D. These are the output from the pocket algorithm. So once if we have the knowledge about the pharmacophore feature, the next step is that we have to, so basically we have two approaches. One is called as grow approach, another one is called as link approach in LigBuilder. So this corresponding for the grow approach and this is for the link approach, right? So let me tell what this image convey that. So this is the binding site. So the binding pocket is having some binding region. So we have a hydrophobic region here. So we have acceptor region here, and we have donor region here, right? So these are the three pharmacophore feature which are identified in the first step of running the pocket algorithm of LigBuilder. So which means that we are very clear that if we want to fit any ligand molecule, so we have to complement both the shape of the binding pocket as well as this pharmacophore feature, right? So first what we do is we take some seed structure. So let us assume this is a seed structure for grow, and this is these are the seed structures for the link approach, right? So first we have to take the seed structure and we have to fit inside the seed structure, and so for the grow approach, right? So let me erase the annotation. So for the grow approach, so the receptor is having a hydrophobic region here, so we have to add some functional group which is hydrophobic in nature. So if we add so to this position, this hydrophobic regions, they can participate in hydrophobic interaction. So here the receptor is having acceptor. So in this position we had to add some donor, some functional group with donor, hydrogen bond donor, and here the hydrogen bond donor is already present. So in this region we have to grow the structure with the help of some hydrogen bond acceptor, right? So here phenyl ring is added to this position. So the phenyl ring is hydrophobic in nature. So if you look at this image, along with the phenyl ring, one more methyl group is added. Again, methyl group is also hydrophobic in nature. So this entire group which can participate in hydrophobic interaction with this hydrophobic binding region of the receptor. So here, as we mentioned, that there is a acceptor. So here, while growing the structure, the algorithm took OH group and put it here. So this OH group now can act as a donor. So it can participate in hydrogen bonding interaction with this acceptor. So already the receptor is having a donor here. So acceptor is added to this position. So this C double bond O, it can act as a hydrogen bond acceptor. So this D can donate the hydrogen bond donor. So both can participate in the hydrogen bonding, right? So finally, if you look at this, let me erase the annotation. So finally, if you look at this, right, so we got a chemical small molecule which is exactly fitted inside the binding site. There are no clashes. It satisfies the shape complementary. Also, it satisfies the stereoelectronic complementary in the sense that the hydrophobic region is complemented with hydrophobic region. Acceptor is complemented by donor, and donor is complemented with acceptor, right? So if we design any ligand molecule, this is what is called as the grow approach. So in case of grow approach, we take the seed structure and we grow in different direction to complement the stereoelectronic properties. But in case of link, it is slightly different. So we will take the pharmacophore feature of the ligand molecule, then we will link those pharmacophore feature with the help of other chemical fragments. Okay, so let me put it in simple words that this is the first pharmacophore feature of the ligand molecule, this is the second pharmacophore feature of the ligand molecule, and this is the third pharmacophore feature of the ligand molecule in its original co-crystallized protein ligand complex. So the pharmacophore feature alone taken, the middle part of the structure is deleted, and if we input this information, right, so the pharmacophore feature is already satisfied by this functional group. So only thing is that we have to change the center part with the help of some other functional group. So here you can see that some other functional group which is inserted here, which make connection between all the three pharmacophore feature, right? So this approach is what is called as the link approach. So basically we can say that LigBuilder has two approach. One is called as grow approach, another one is called as the link approach. For this demonstration purpose, I am going to demonstrate you only the grow approach, not the link approach, right? So I ask you to practice the link approach on your own. So coming to what are the various softwares which are required. So for doing this experiment exercise, we need LigBuilder. So LigBuilder, we have different version. For this demonstration purpose, I have used this version called as version 1.2. So I highly recommend you to download the same version from this website. So it is freely available for academic. And another important thing is that this software can be used only in Linux. We cannot use this on Windows, very important. So for practicing this exercise, for running this, you should have Linux installed computer, right? So I'm going to demonstrate using Ubuntu. So any version of Linux will work, doesn't matter. So what are the needed files? So we need 4 files. In which I'll be using 3 for grow. So grow approach. So the first file is 4dfr.pdb is the protein molecule, 4dfr.mol2 is the ligand molecule, 4dfr underscore grow is the seed structure for grow, and 4dfr underscore link is the seed structure for the link approach. So I'm not going to use this file because I'm going to demonstrate only the grow approach using this 4dfr grow, 4dfr mol2 and 4dfr.pdb. So I highly recommend you to practice the link. The methodology is going to be completely same. The only difference is the the algorithm, right? So the script file is going to get changed for the for running the grow and link. I'll show that in the demonstration, right? So that is the basic idea of LigBuilder, right? So I think we can go for the demonstration now. Hello. So in this session I am going to demonstrate you how to use LigBuilder for generating the novel ligand molecules. As we know that we have 2 approaches in LigBuilder. One is called as grow approach, another one is called as link approach. So let us start with the grow approach. So I kept all the needed files in desktop inside the folder called as LigBuilder. For the same folder I gave access in Google Classroom. So these are the folders which are present inside LigBuilder folder. We have bin, forbidden.mdb, fragment.mdb, grow, or link, Mozilla installer, needed files, parameter, pocket, process, toxicity.mdb. So inside this needed files, I kept all the needed file for this exercise. So 4dfr.pdb is the protein molecule, and 4dfr.mol2 is the 4dfr.pdb is the protein molecule, 4dfr.mol2 is the ligand molecule. So it's actually a complex. 4dfr is a complex molecule, complex made between the protein and ligand molecule. So what I did is I separated the protein and ligand molecule and saved the protein as 4dfr.pdb and the ligand molecule as 4dfr.mol2. And these two files are 4dfr underscore grow.mol2 and 4dfr underscore link.mol2. So these are the seed structure for grow and link. So for grow, the seed structure is 4dfr.mol2, and for link, the seed structure is the 4dfr link.mol2. So later I'll teach you that how to create this seed structure for grow and link. So we are going to, there is no graphical user interface for running this LigBuilder. So everything we are going to run with the help of terminal. So let me first copy the protein in its PDB format and the ligand molecule, co-crystallized ligand molecule in its mol2 file format. So these two files I am copying, and I am going to paste it inside the folder called as pocket as the first step. So very first step is we have to run this pocket. So for running this pocket, we need two input file. One is the protein structure in its PDB file format, and the co-crystallized ligand molecule, the separated co-crystallized ligand molecule in its mol2 format. So in our case, 4dfr.pdb is the protein molecule and 4dfr.mol2 is the co-crystallized ligand molecule. So we have to run the pocket. So for running the pocket, the program is pocket, and first we have to tell the program that what are the input files and where the input files are present. So we have to edit this file called as pocket.index. So I am opening this file with text editor. So here first input file is the PDB file. What is our PDB file name and where that file is present? So I kept this 4dfr.pdb in home, quorum, desktop, LigBuilder inside the folder pocket. So inside the pocket I have this 4dfr.pdb. So I gave the path for 4dfr.pdb. So similarly, what is the ligand file name? So the ligand file name is 4dfr.mol2, and what is the path for that? So here this is the path for 4dfr.mol2. So inside home, inside quorum folder, inside desktop, so inside LigBuilder, inside pocket, I kept this 4dfr.mol2. So parameter directory, where the parameter directory is present. So actually if I go one step back, the parameter folder is present inside the LigBuilder folder. So what I did is I gave the path for the parameter folder, home, quorum, desktop, LigBuilder, parameter, not inside the pocket, outside. Okay, one folder below the pocket folder. So next is, these are the output files which we will get. So we have to mention where this file should be written and what should be the file name. So it is going to generate pocket.txt and grid.txt, two text files. So I gave the name like 4dfr underscore pocket.txt, 4dfr underscore grid.txt. The name can be anything. So I directed this file to the same current directory, pocket. So I requested the software program to output this 4dfr pocket.txt and 4dfr grid.txt to the same folder inside pocket. So it is also going to generate three more files related to pharmacophore. One is called as 4dfr keysite.pdb, another one is 4dfr pharmacophore.txt and 4dfr pharmacophore.pdb. So totally we will get files as the output file if we successfully run this pocket.index with the help of pocket. So I directed all the files, these three files, pharmacophore related files, also to the folder pocket. So all the 5 output files will be written inside the folder pocket. So these are the changes that you have to make, right? So already I made the changes. So these are the changes what you have to make, and save the file, Ctrl S, and we are ready for running this pocket dot index with the help of pocket. So for running the program, first thing is you have to go to the folder where you have the input files. All right. So for running the pocket, so the two input files are 4dfr.pdb and 4dfr.mol2. So inside the folder, I am going to open a terminal. Okay, so I have opened the terminal. So I am going to give ls to see. Okay, so I am going to give dir to see what are the various files which are present within the folder. So I ensure that the input files and the program is present. So pocket is the program we are going to run. Okay, so the input files are 4dfr.mol2 and 4dfr.pdb, and all the input file details and output file details we have written in the file called as pocket.index. So let me show how to run the program. So for running the program, So what we had to give is we had to give the command dot slash pocket. Okay, so first you without the script file we will try to execute this command. Okay, so it says that error, no index file is given for pocket. So for running the pocket, the command is dot slash pocket. Okay, so just like modular mod 10.1, so here the command is dot slash pocket is for running the pocket. It is asking for the index file. So the index file is pocket.index. So I'm going to give like dot slash pocket space pocket.index. Okay, so this is a command for running this pocket. Okay, so we are ready for running pocket.index with the help of pocket program. So let's run it. Yeah, it is running. So now you can see the job is successfully completed. Pocket has done the job successful. So if it is not successful, that will be displayed here. Okay, so which means that you have to do some modification and somehow you have to make the program to run correctly. So what this pocket does is it calculated the pharmacophore feature that is present in the ligand molecule as well as in the binding site. So those informations are written here as pharmacophore.text and pharmacophore.pdb and key site.pdb grid.text, right? So these are the output files. As we said, we got 5 output files. So in my computer the PyMol is not opening in Linux. So if you have access for PyMol, you can open this PDB file. You can open this pharmacophore.pdb. You can check the pharmacophore which is identified in this step, right? So moving on to the next step. So the next step is once if we run the pocket successful, so now we have 2 options. Okay, so either we can go for grow or we can go for link. So first we'll finish the grow. So we go to the grow folder and we open grow.index file. So because this is the file which we are going to edit for running the grow program. So I'm opening this file using text editor. So now we have to change this. Okay, for the first step I already made the changes. For this we have to make the changes. So we got some output file in the previous step. Okay, so one is pocket.txt, another one is grid.txt, right? So if we look at those 2 files in pocket folder, the output from the previous step, the file names are 4dfr pharmacophore.txt. Okay, 4dfr pocket.txt. So here I am going to change this 4dfr pocket.txt. So it is not 1dwd, 4dfr pocket.txt. Also we have 4dfr grid.txt in pocket folder. That is also one of the output from previous step, 4dfr grid.txt. So this is the seed structure for grow. So seed structure for grow is 4dfr underscore grow.mol2, right? So this 3 files first we will copy and paste it inside the grow folder, 4dfr pocket.txt, 4dfr pocket.txt, 4dfr grid.txt. These 2 files I am copying and paste it inside the grow folder. So inside the grow folder I have pasted, and one more file which I have to copy is 4dfr grow.mol2. So 4dfr grow.mol2 is present in the needed files. 4dfr grow.mol2 is the seed structure for grow. So I copy that also and paste it inside the grow folder. So if you look at, I copied all the 3 files inside the folder called as grow. So the location is not correct, so I am going to delete the location and I am going to change the location of the all these input files. Okay, so all this file I have inside the folder called as grow. So let me check what is the path for this folder. So I copy this location of the grow folder and I am going for this editor and I paste the location. Okay, so inside the grow folder I have 4dfr grow. Inside the grow folder I have 4dfr pocket.txt. Inside the grow folder I have all the 3 input files I have, right? So where we have the parameter file, we have the parameter file inside the LigBuilder, not inside grow folder. So I have given the path for that. So where we have parameter.mdb, so parameter.mdb also present inside the main folder LigBuilder. So where do we have forbidden.pdb? The forbidden.pdb folder, you can check, that is also present inside the main folder called as LigBuilder. So where do we have toxicity.mdb? So toxicity.mdb is also present in the same place. Inside the LigBuilder folder, right? So these are the changes which we have to make, and the final output file population.lig and ligands.lig file will be written here. We are not going to change any parameter as a beginner, right? So if you are advanced user, we can tweak the parameter. I'm not going to change any parameter. So if I run this program successfully, it's going to output population.lig and ligand.lig file inside the same folder grow. So I am saving this by clicking Control S. So I just okay, so I save this file and I minimize this. So I'm going to run now this grow. Okay, so for that I am opening a terminal. So the command now is I am going to give /grow. Okay, so command is /grow. So correct usage is it is saying that we have to use grow.index file. So I just give /grow space grow.index and let me run this. So it is saying that fragment.mdb it is not able to locate the index file. So let me go to the folder. So I kept all the files in desktop inside LigBuilder. So the error what we got is fragment.mdb. So here we have fragment.mdb folder. So it's saying there is no file called as index because here it is given like small letter. So we had to change this to capital letter index. Just rename it. So similarly, we can change for index fragment forbidden.mdb also we had to change this to just rename this to capital index INDEX, rename it, and also do the same thing for toxicity.mdb. So toxicity.mdb has one index file, so just rename this to capital index INDEX, rename it, right? So let's run it again. Okay, we'll check whether the program is running or not. Yeah, it is running. Here you can see now the program is running and it is generating the population. So it is a time consuming process because we requested the software to generate 200 novel ligand molecules based on the ligands which are satisfying the pharmacophore feature. So it is generating the population and we had to wait for the completion of this. So it may take some time. Okay, so we had to wait for the completion. Okay, the process is successful. Now we can see here LigBuilder has done the job successfully. So it took approximately less than 30 minutes on my computer. So let me go to the folder. So let me go to the grow folder. So here two output files which are population.lig and ligands.lig, right? So these are the files in which all the newly generated ligand molecules or details of those ligands are written here. So let me show this. Open with the text editor. So here you can see the small molecule, right? So all the details of the newly generated molecules are written inside this folder. I'm closing this file. So and I just go to the next step. The next step is we have to process. So since all the ligand molecules are written in the same file, we have to process it. We have to separate those ligand molecules into individual file. So for that we go for the folder called as process. So we are going to edit the file process.index using text editor. So there is nothing to edit, just we have to copy this ligand.lig file into this into this process folder. So once if we run this, it is going to generate all the results inside the folder called as results.mdb. So let me copy the file from the grow folder ligand.lig. So this is the file which we need. We will copy and paste this file to the folder called as process. Paste this file, and we have to just run this process.index because nothing to change in this script file. So we just open the terminal and we just give /process. Okay, so it will ask you to input the script file, index file. So we have to give like /process space process dot index, right? So this is the file. So this is a command for running this, and so let's run this. So if we run, you may get some output like segmentation fault. Results.mdb does not exist. Okay. So what we have to do is once again we have to run the same command /process space process.index, and this time it will run and it will generate all the it will write all the output files to this folder called as results.mdb. So here we got the results.mdb folder. So inside you can see many numbers of mol2 file, right? So we got 200 mol2 files. So which means that we requested the software to output 200 novel ligand molecules. So all the 200 novel ligand molecules which are written inside this folder, and it has an index file. So this is a very important file which has the details of all the newly generated molecules, 200 molecules. And I am going to copy this file. So here each column is given here. The header for each column is given here. So ID of the molecule is the first column. Second column is the name of the mol2 file. This is the name of the mol2 file. And third column is the family of the molecule. So fourth column is the molecular weight. Formula. Fifth column is the molecular weight. Sixth column is the log p value. So this is the log p value, and seventh column is the binding score or pKd, and the last column is the chemical score. We have chemical score, right? So using this file we can do kind of analysis. So